king, queen, prince, banana. Suppose a tokenizer assigns them the IDs 4217, 88, 10982, and 3. Those numbers look useful, they aren't, not yet. Token 4217 is not more royal than token 3, and token 88 isn't closer in meaning to 89 than to 10982. The IDs are shelf numbers. They tell the model where to look, but they don't describe what it will find. So how does an LLM get from an arbitrary label to a representation where king can end up near queen while banana lives somewhere else? The answer is an embedding, a list of learned numbers that gives each token a starting location in a much larger space. That sentence hides 3 problems. Why use a list instead of one number? Who chooses the values? And when one token has 2 meanings, as bank does, which meaning goes into the list? We'll solve all 3. Start with the most obvious representation possible. Imagine a toy vocabulary with 6 tokens: king, queen, prince, government, apple, and banana. Build a panel with 6 switches. King turns on the first switch and leaves the other 5 off. Queen turns on the second. Banana turns on the 6th. This is called a one-hot vector. It identifies every token perfectly. No 2 tokens share the same pattern. It also knows nothing about relationships. King and queen differ in one active switch. King and banana also differ in one active switch. Under this representation, every distinct pair is equally unrelated. The panel can say which token arrived, but it cannot say that queen is used more like king than banana is. Then scale the wall to a vocabulary with tens of thousands of entries. Every token needs a vector with tens of thousands of positions, almost all of them 0. It is a huge identity card with no learned geometry. The useful part is not the wall itself. It is what happens when that one active switch is connected to a smaller bank of trainable numbers. Picture an embedding table as a cabinet. One drawer for every token in the vocabulary. Each drawer contains a strip of numbers. When token ID 4217 arrives, the model opens drawer 4217 and pulls out that row. The row might contain hundreds or thousands of values, depending on the model. That row is the token's input embedding. Mathematically, multiplying the giant one-hot vector by the embedding table selects the same row. Real implementations normally skip the giant wall and perform the lookup directly. This fixes the size problem. Instead of carrying one slot for every vocabulary item, the token gets a dense vector with a fixed width. Nearly every position can hold a useful value. But look inside the drawer at the start of training, and the values are not a definition of king. They don't say crown, ruler, royal, or male. They begin as an initialization. The model has not been handed a human dictionary for its coordinates. Meaning is not typed into the table. The table is adjusted because the model keeps making predictions and keeps being wrong. Return to our 6 tokens. Place their vectors as points on a simple 2-dimensional map so we can watch them move. Real models use many more dimensions. This flat map is only an illustration. At first, scatter the points. King might sit beside banana. Queen might be alone in a corner. The arrangement has no useful structure. Now train the model on text. King appears near words about rulers, palaces, governments, and crowns. Queen appears in many related surroundings. Apple and banana repeatedly appear around fruit, food, and eating. Each prediction creates an error. Training sends small adjustments through the model, including into the embedding table. One update barely changes anything. Repeated across enormous amounts of text, those nudges reorganize the space. The model is not commanded to put royalty in one neighborhood and fruit in another. It is rewarded for making better predictions. Geometry emerges because reusing related features can help with that objective. This is the distributional idea behind classic methods such as word2vec and glove. Words used in related contexts can acquire related vectors. Modern LLMs learn their token embeddings jointly with the rest of the network, but the basic reveal survives. The numbers become useful through training. Useful does not mean tidy. Antonyms can appear in similar sentences. Grammar, topic, frequency, and bias can all shape the same space. Nearness is evidence of a learned relationship, not a certificate that 2 words are synonyms. Once training creates structure, we can compare vectors. One option is distance. Another is direction. Cosine similarity compares the angle between two vectors, which often helps find tokens pointing in similar directions even when their lengths differ. On our map, king, queen, prince, and government may form one broad neighborhood. Apple and banana may form another. A direction that moves from king toward queen may resemble a direction from prince toward princess. This is where the famous equation appears. King minus man plus woman lands near queen. It is a striking demonstration, not a law of language. The result depends on the embedding model, training data, vocabulary, and method used to judge the nearest answer. Change the setup and the arithmetic can weaken or fail. The safer lesson is smaller. A trained vector space can contain useful regularities in neighborhoods and directions. It gives the model something richer than an arbitrary ID. And it gives our thumbnail its answer. King and queen are close because training found it useful to represent patterns they share. Banana participates in different patterns, so it tends to occupy a different region. But the map is about to mislead us in a new way. A two-dimensional drawing invites us to label the horizontal axis royalty and the vertical axis food. That is usually not how a real embedding works. A model may use hundreds or thousands of coordinates, and one human concept can be distributed across many of them. A single coordinate can also participate in several patterns. The features are entangled. There is a simple clue. Rotate our whole map without changing the distance between any pair of points. Every coordinate changes, but the neighborhoods remain. King is still near queen. Apple is still near banana. The relationships survive even though the axes point somewhere new. Researchers can find directions or internal features correlated with concepts. That does not mean coordinate 17 is the royalty dial and coordinate 83 is the fruit dial. The flat picture has another limitation. It is a projection, like pressing a globe onto a sheet of paper. Some neighborhoods look distorted because a high-dimensional space has been squeezed into two dimensions. And the geometry can preserve ugly patterns from its training data. Static word embeddings have famously reproduced social stereotypes. A learned map reflects statistical structure in data, including structure we may not want. So an embedding is not a clean dictionary of meaning. It is a learned numerical starting point with useful, messy relationships. That word, starting, matters most for the final problem. Take these two sentences. She deposited money at the bank. They sat beside the riverbank. Assume the tokenizer uses the same token ID for bank in both sentences. At the embedding table, both copies open the same drawer. Both receive the same starting token embedding. That single lookup row cannot know whether this sentence involves loans or water. It has not interacted with deposited, money, river, or sat beside. Then, the token enters the transformer layers. In the first sentence, information from deposited and money changes the internal state associated with bank. In the second, river and beside push it in another direction. After contextual processing, the two bank tokens no longer have identical representations. This is the distinction that gets blurred whenever people say, the embedding for this word. The input token embedding is the learned row selected before contextual interaction. A contextual representation is the later vector after the model has processed this occurrence alongside the other tokens. Classic static word embeddings assign one fixed vector to a vocabulary item. Transformer models create changing hidden states for each occurrence as information moves through the layers. The starting embedding does not choose the correct sense alone. It gives the token a learned place to begin. Now, the route from ID to meaning is visible. The tokenizer produces an arbitrary integer. That integer selects one row in an embedding table. Training adjusts the row with the rest of the model until its coordinates help prediction. The resulting space can carry useful neighborhoods and directions, but its dimensions are distributed, imperfect, and shaped by the data. Then context changes the representation again. So words do not become meaning because someone assigns them clever ID numbers. They become task-useful vectors because prediction repeatedly reshapes the table, and because later layers let each token interact with the sentence around it. That resolves our map. King can begin near queen, while banana begins elsewhere. Bank can start from one row and end in two different contextual states. But we have left the most important machine unopened. How does bank decide that money matters in one sentence and river matters in the other? How does each token choose which other tokens should influence it and by how much? That is the job of attention.